Today we're going to look at using vectors to solve geometric proofs. So a few things to keep in mind, some ideas. Usually a good idea, or handy, if you use one of the vertexes in the polygon, or whatever you're working with, as the origin. So some key point there, so you can sort of treat that as the origin, so you can create position vectors and things like that. Always remember that sum and difference of vectors creates a triangle. Parallel vectors are scalar multiples or multiples of each other. Angle between vectors, now we can use the dot product to find that sort of thing. Perpendicular vectors, well, they'll have a dot product of 0. And whenever you're trying to work out what the position vector is, head minus tail, head minus tail. So let's look at a couple of examples. We're going to prove the diagonals of a rhombus are perpendicular. So OABC, notice conveniently I've made the vertex down the bottom there, I've called it O to really highlight. I'm going to use that as the origin. So OABC. Any vector coming from A, I'm basically going to label all of the position vectors. So OA would be a position vector, I'm going to call it A. OC is a position vector, I'll call it C. Now the diagonals, OB and AC. Well, OB then becomes A plus C. And the other one is the difference. I've made it AC. So if it's AC, head minus tail, C minus A. But I could have just as easily made it vector CA and then it'd be the other way around. It doesn't really matter for this proof. So now let's have a look at the dot product of vector OB and AC. Remember, we're trying to prove that they're perpendicular. And we expand it out, just like normal rules of algebra, but instead of multiplying its dot product, C dot C minus A dot A, difference of two squares. But we saw that C dot C is the same as the magnitude of C squared, and A dot A would be the magnitude of A squared. But hang on, this is a rhombus. Therefore, the magnitude of OA must be the same as the magnitude of OC. Well, there it is then. So C squared minus A squared must be 0, because those magnitudes are the same. So the dot product's equal to 0, which means those two vectors, or the diagonals in this case, are perpendicular. Let's prove Pythagoras' theorem. I mean, there are so many ways of proving Pythagoras' theorem, and you've probably seen a few of them. Well, now let's do it using vectors. So there's a right angle triangle. I've made the right angle, that vertex, I've called it O. So that's going to be my reference point. So OAB is a right angle triangle. I'll call OAA and OBB. Well, the hypotenuse then would be head minus tail, B minus A or A minus B, whichever way you want to do it. I've gone B minus A. Okay, we're going to try and prove Pythagoras' theorem. Remember, OA, notice that's not the vector OA. I'm talking about the length OA there. And that's why the arrow is important. So are we talking about the vector, or are we just talking about the side of a triangle? In this case, I'm just talking about the length of the side of the triangle. So OA squared plus OB squared. That would be the magnitude of A squared plus the magnitude of B squared. Well, what about the hypotenuse, AB squared? It's going to be the magnitude of B minus A squared. But that I could rewrite as B minus A dot B minus A. Expand that out, I get B dot B minus 2 lots of A dot B plus A dot A. But hang on, it's a right angle triangle. So I know OA is perpendicular to OB, therefore A dot B must equal 0. So I now know that AB squared is B dot B plus A dot A, which is magnitude of B squared plus magnitude of A squared, same as we found over there. So yes, Pythagoras' theorem must be true. AB squared is OA squared plus OB squared. Here's our shape. A, B, C, D. P, Q, R and S are all midpoints. What type of quadrilateral would we get if we joined P, R, Q, S? Now you might be able to tell, because I've pretty much drawn that one to scale. I've put those midpoints in the right spot. So you might be able to look at it and kind of work out what type of quadrilateral we might be getting here. You'll notice I haven't got an O labelled on the diagram, so I'm going to treat A. That's going to be my origin, if you like. So all the vectors coming out from A will be position vectors. I'll call them, so AB I'm going to call U, AC I'm going to call V, and AD I'm going to call W. So they're the three position vectors I know in this shape. So the vector AP would be half of the vector AC. Therefore, it's a half of V. Now for Q, I'm actually coming from B, if you see. So it's BQ is well, not my reference point, but I'm saying that BQ would be half the vector BD. But BD would be head minus tail, so it's W minus U. AR, so let's find R. Well, R's lying on the vector AD, so it would be half of W. And S, that one's lying on the vector BC, so I'm actually talking about the vector BS here. It would be half of, oh, that's wrong. I've got AC there, of course, it should be BC, shouldn't it? So half of BC, and that'd be half of head minus tail, V minus U. Okay, so there's the four that I need to do this. So now I'm going to look at the vector PR. I can get that by smashing together PA and AR. So if I add PA and AR, well, PA is the negative of AP, so that's minus a half V, plus AR we found was a half W, so we get a half of W minus V. The next vector we're going to try and find is SQ. That one is when we can join together SB and BQ. So SB, that'll be the negative of BS, so we'll get a half of U minus V, and then we'll add BQ, which is a half of W minus U, and we once again end up with a half W minus V. So that means that the vector PR is equal to the vector SQ, and that's enough to prove it's parallel, because if those vectors are equal, one, they must be parallel, but two, they also must have the same length. So PRQS is a parallelogram, as we have a pair of opposite sides, both equal and parallel. That's going to do us for our theory today. And we got a triple.